Welcome to our exploration of data collection, storage, and computing using cloud platforms in the world of IoT. In this video, we'll break down how physical devices interact with cloud services, the evolution from traditional storage to modern cloud-based solutions, and the key technologies that make it all possible. Whether you're new to IoT or looking to deepen your understanding, this journey will help you see how data moves from sensors to the cloud and back, powering smart applications everywhere. Let's start by understanding the basics of IoT devices and the role of cloud computing in this ecosystem. The heart of every IoT system are physical devices and endpoints. These devices are equipped with sensors and actuators that collect data from their environment, like temperature, humidity, or light intensity, and can also act on the world around them. The collected data is then sent to other devices or directly to cloud-based servers for further processing. Seamless communication between the physical and digital worlds is what makes IoT so powerful, enabling automation, real-time monitoring, and smarter decision-making across industries. Before the rise of cloud computing, data from IoT devices was typically stored locally. This could mean saving data on removable media like micro-SD cards or on local servers dedicated to device nodes. Sometimes, data was managed by a coordinating node within a distributed database management system, DBMS, or even sent to remote nodes in a distributed DBMS. As the need for scalability grew, organizations began saving data on enterprise servers or data centers via the internet, paving the way for more centralized and accessible storage solutions. Today, data collection methods have evolved significantly. IoT devices now often communicate directly over the internet, sending their data to cloud-based storage or enterprise data centers. This shift allows for real-time data access, improved scalability, and centralized management. Cloud platforms can aggregate data from countless devices, making it easier to analyze trends, generate insights, and automate responses. This modern approach is essential for supporting the massive scale of today's IoT deployments. Navigate the world of IoT and cloud computing. It's important to understand some key terms. A resource can be anything that can be read, written, or executed, such as files, databases, or even path specifications. A system resource refers to core components like the operating system, memory, network, server, or software applications. These resources are the building blocks that enable devices and applications to function and interact within a cloud environment. Next, let's clarify environment and platform. An environment is the setting where programming or program execution occurs. Think of Windows or Google App Engine. A platform, on the other hand, is the combination of hardware, operating system, and network that supports software applications or services. Understanding these terms helps you see how IoT devices and cloud services interact, ensuring applications run smoothly across different setups. Edge computing pushes data processing closer to where data is generated, right at the IoT device or sensor. This reduces latency and enables faster responses. Distributed computing, meanwhile, spreads resources and processing tasks across multiple environments over the internet. Both approaches are crucial for handling the vast amounts of data generated by IoT devices, ensuring efficient processing and reliable service delivery. In cloud computing, a service is software that provides specific capabilities, logically grouped and encapsulated for use by applications. Services are called by applications to utilize these capabilities, making it easier to build complex solutions by combining different functionalities. This modular approach is at the core of cloud platforms, allowing developers to focus on innovation rather than infrastructure management. Web computing leverages resources from web servers or web services over the internet, making applications accessible from anywhere. Grid computing pools interconnected resources, forming a grid that replaces traditional web servers for large-scale processing. Web services are applications identified by URLs, described using XML-based languages, and interact with other services via internet protocols. These technologies form the backbone of scalable, interoperable cloud solutions. XaaS, or anything as a service, is a software architectural concept that enables the deployment and development of applications as services. Using web and service-oriented architecture, SOA, XaaS allows organizations to offer a wide range of services, from infrastructure to software, over the internet. This flexibility is key to the rapid innovation and scalability seen in modern cloud environments. Cloud computing paradigm is built around delivering a collection of services over the internet. These services provide computational functionality and are deployed using the infrastructure of a cloud service provider. The underlying infrastructure may use utility, grid, or web services environments, including networks, systems, and data centers. This setup is often compared to electricity supply. Users access resources as needed, without worrying about the underlying complexities. Cloud platforms connect devices, data, APIs, applications, services, people, and businesses. They offer a virtualized environment, which appears as a single running environment to all applications and services, even though multiple physical environments may exist. This abstraction allows for seamless integration, scalability, and flexibility, making it easier for organizations to deploy and manage complex IoT solutions. Virtualization is a cornerstone of cloud computing. It enables the provisioning of storage, network functions, servers, and desktops across multiple platforms and servers. Applications and services can execute independently of the underlying hardware, requiring only internet connectivity to the cloud platform. This independence allows for greater flexibility, resource optimization, and easier management of diverse computing environments. There are several types of virtualization in cloud computing. Storage virtualization allows applications to access physical storage through abstract interfaces. Network function virtualization makes multiple networks appear as a single network to applications. Server virtualization enables applications to access multiple servers as if they were one. These techniques collectively enhance resource utilization and simplify management. Virtualized desktops allow users to deploy and manage multiple desktop environments, even if they are accessing them through their own computer platforms. This means users can work across different operating systems and platforms, or even remote computers, all from a single interface. This flexibility is especially valuable for organizations with diverse computing needs. Cloud computing offers a range of powerful features. Users benefit from on-demand self-service, resource pooling in a multi-tenant model, broad network accessibility, elasticity, massive scale availability, scalability, and maintainability. These features make cloud platforms ideal for supporting the dynamic and growing needs of IoT applications and services. Additional advantages of cloud computing include homogeneity, advanced virtualization, interconnectivity platforms, resilient computing, advanced security, and low cost. These benefits help organizations reduce operational complexity, improve security, and lower expenses, all while delivering reliable and high-performance services to users and devices. Despite its many advantages, cloud computing also presents some concerns. These include the need for a constant high-speed internet connection, limitations in available services, potential data loss, non-delivery as per service level agreements (SLAs), differences in APIs and protocols across clouds, security challenges in multi-tenant environments, and loss of user control. Addressing these concerns is essential for building trust and ensuring reliable cloud services. Cloud deployment models define how cloud resources are made available and who can access them. The main models are public, private, community, and hybrid clouds. Each model offers different levels of accessibility, security, and control, allowing organizations to choose the best fit for their needs and compliance requirements. Public clouds are provisioned by institutions, industries, or businesses and are open for public use. Private clouds, on the other hand, are exclusive to a single organization, providing greater control and security for employees and associated users. The choice between public and private clouds depends on factors like data sensitivity, compliance, and organizational needs. Community clouds are designed for use by a specific community of organizations with shared concerns, such as security and compliance. Hybrid clouds combine two or more distinct cloud types, public, private, or community, allowing organizations to leverage the benefits of each while maintaining flexibility and control over their data and applications. Cloud services can be viewed as distribution services that link computing functions, data stores, processing functions, networks, servers, and applications. XaaS Anything as a Service encompasses a range of service models, each designed to meet specific needs, from software delivery to infrastructure provisioning. This approach streamlines resource management and accelerates innovation. Software as a Service (SaaS) delivers software applications over the internet on demand. The cloud provider manages software control, maintenance, updates, and infrastructure, freeing users from these responsibilities. SaaS is ideal for end users who need access to applications without worrying about installation or maintenance, making it a popular choice for businesses of all sizes. Platform as a Service (PaaS) provides a platform for developers to build, deploy, and manage applications. The cloud provider handles the platform, network, resources, maintenance, and security, allowing developers to focus on creating and running their applications. PaaS accelerates development cycles and simplifies the deployment of scalable, cloud-native solutions. Infrastructure as a Service (IaaS) offers on-demand access to computing infrastructure, such as data stores, servers, data centers, and networks. Developers can install operating systems, data stores, and applications, and control them as needed. IaaS is typically billed on a pay-as-you-go basis, making it cost-effective for organizations that need flexible, scalable infrastructure. Data as a Service (DaaS) makes data stores or data warehouses available over the internet on demand. Enterprises can access, replicate, and manage data without handling the underlying infrastructure. The data center provider is responsible for power, control, network, maintenance, scaling, and security, ensuring reliable and secure data access for users. XIVELY, now owned by Google, is an open-source IoT platform that provides connectivity for devices like Arduino. As a commercial PaaS, XIVELY acts as a data aggregator and mining platform, supporting protocols like REST, WebSockets, and MQTT. It enables real-time data collection, visualization, and integration with the Web of Things, making it a powerful tool for IoT developers and businesses. XIVELY offers a range of services, including real-time data collection, data visualization, graphical plotting, alert generation, and access to historical data. It supports programming languages like Java, Python, and Ruby, and integrates with platforms such as ARM and Arduino. XIVELY APIs enable seamless interaction with devices and cloud services, making it easy to build and manage IoT solutions. XIVELY uses the concepts of users, feeds, data streams, data points, and triggers. A feed represents a location, with data streams for each sensor. Data can be captured using a pull method, automatic feeder, or a push method, manual feed. This flexibility allows for efficient data collection from a variety of IoT devices and environments. Data stream in XIVELY is a continuous flow of sensed data over the internet. Data points are individual values, while triggers are actions taken when certain conditions are met, such as a sensor reading falling below a threshold. XIVELY enables real-time data visualization, graphing, and access to historical data, making it easy to monitor and respond to changes in the environment. NIMBITS is an open-source distributed cloud platform for IoT based on a PaaS model. It deploys instances of the NIMBITS server at device nodes, functioning as a data store, collector, and logger. NIMBITS supports access to historical data and is designed for both machine-to-machine (M2M) and human interaction, making it a versatile choice for IoT projects. NIMBITS offers edge computing capabilities, running rules and pushing important data to the cloud when connected. It supports multiple programming languages, including Arduino, JavaScript, and HTML, and can be integrated with various hardware platforms. This flexibility allows developers to build local applications that interact seamlessly with cloud services. NIMBITS server functions as a backend platform, relaying data between software systems and hardware devices. It features a rule engine for connecting sensors, people, and software to the cloud and each other. Rules can trigger calculations, statistics, email alerts, push notifications, and more, enabling intelligent automation and responsive IoT solutions. NIMBITS provides robust data logging services, storing historical data points and objects in formats like JSON or XML. It filters noise and highlights important changes, sending them to central instances as needed. NIMBITS also offers data visualization tools for connected sensors, including time and geostamping, making it easy to monitor and analyze IoT data. NIMBITS clients enable real-time data collection, charting, and graphical plotting of collected data. The platform supports alert subscriptions and real-time notifications, creating streams of data objects that can be monitored and accessed from anywhere. This capability is essential for shaping the behavior of connected devices and software-based IoT solutions. NIMBITS supports a wide range of hardware platforms, including Mbed, Arduino, and Raspberry Pi. Its web service APIs are easy to implement on device hardware, enabling seamless data collection and transmission to the cloud. NIMBITS can be deployed on Google App Engine, J2E servers, Amazon EC2, or Raspberry Pi, offering flexible deployment options for diverse IoT environments. Sensing is a fundamental building block of IoT devices. Sensors, either on board or attached, collect various types of information such as temperature, humidity, or light intensity. This data can be communicated to other devices or cloud-based servers for further analysis and action. Accurate sensing is crucial for enabling automation and real-time decision-making in IoT systems. Actuation allows IoT devices to interact with the physical world. Actuators, such as relay switches, can take actions based on commands received from the device or cloud. For example, an IoT device can turn an appliance on or off in response to sensor data or remote instructions. This capability is key to creating responsive and intelligent IoT systems. Communication modules in IoT devices are responsible for sending collected data to other devices or cloud-based servers, and for receiving data or commands from remote applications. Reliable communication ensures that data flows smoothly between devices and the cloud, enabling real-time monitoring, control, and analysis. Analysis and processing modules make sense of the data collected by IoT devices. These modules can run locally on the device or in the cloud, transforming raw sensor data into actionable insights. Effective analysis and processing are essential for enabling smart applications, predictive maintenance, and automated decision-making in IoT ecosystems. Raspberry Pi is a low-cost, credit card-sized mini-computer that runs various flavors of Linux. It can perform most tasks of a regular computer and allows interfacing with sensors and actuators through its general-purpose I/O pins. Raspberry Pi supports Python out of the box, making it a popular choice for IoT prototyping and development. Raspberry Pi 2 Model B features a 700 MHz ARM processor, 512 MB SDIM, 2 USB 2 ports, an Ethernet port for internet connectivity, and HDMI output for video and audio. These hardware features make it versatile for a wide range of IoT applications, from data collection to device control and automation. This model includes a composite video output, a 3.5mm audio jack, and a variety of GPIO pins for input-output operations. It also features interfaces for I2C, SPI, UART, and DSI for connecting displays and other peripherals. These interfaces expand the possibilities for integrating sensors, actuators, and displays in IoT projects. Camera Serial Interface, CSI, allows the Raspberry Pi to connect to camera modules, enabling image and video capture for IoT applications. The device also includes 5 status LEDs for monitoring system activity, providing visual feedback for developers and users. Raspberry Pi does not have built-in storage or an operating system. Instead, it uses an SD card slot for storage, allowing users to load a Linux image. Power is supplied via a micro-USB connector, making it easy to deploy in various environments. This design keeps the device compact and flexible for different IoT scenarios. Raspberry Pi supports several Linux distributions, including Raspbian optimized for Raspberry Pi, Fedora Fedora-based, RaspBMC OpenELEC and RISC OS. These operating systems provide a flexible environment for developing and running IoT applications, supporting a wide range of programming languages and tools. In summary, the integration of IoT devices with cloud platforms has revolutionized data collection, storage, and computing. From traditional local storage to advanced cloud-based solutions, organizations now have the tools to build scalable, flexible, and intelligent systems. Platforms like XIVELY and NIMBITS, along with versatile hardware like Raspberry Pi, empower developers to create innovative IoT applications that connect the physical and digital worlds. As IoT and cloud technologies continue to evolve, we can expect even greater advancements in connectivity, automation, and data intelligence. The ongoing development of new platforms, protocols, and devices will further expand the possibilities for smart environments, from homes and cities to industries and beyond. Staying informed and adaptable is key to leveraging these technologies for future success.